Good morning. Happy Republic Day. I would like to thank all of you who responded to my earlier post requesting me to continue the series. See, once in a while, you are not very sure in the sense that whether one should do continue or not, because there are just, you look at YouTube, there just to be just too many such videos, so you begin to wonder whether you are doing anything which is worthwhile to the students. Okay, anyway, so now that we started, let's do it. So as I said in the last lecture, today we are going to look at the space of all integrable functions on a given fixed closed and bounded interval. So let us get started. I'll share the video. Yeah. So let us fix an interval a, b in R, and alpha is a bounded function from, okay, just bounded. We are not assuming to start with it's increasing, okay, not necessarily increasing at present. As we go, we may have to assume, but at present I don't want that. Okay, so we want to denote by R of alpha this set of all functions a, b to R, so that f is alpha integrable. So notice that in particular f must be bounded also, and then interval a to b f d alpha makes sense. Okay, right. So we want to study the properties of this space. First, notice that this is non-empty because 0 of course is there, and we actually said that any constant functions are there, and we also proved all continuous functions are there. That is continuous function from a, b to R. Right? Do you remember all those things? Okay. What else did you prove? Okay. Yeah. So we proved all these things. So this is not a small class. This set of all such functions are very big. What we want to first do is that it is a vector space. So the first observation we want to make is alpha is a vector space over R. What does it mean? That means if you give me lambda mu scalars in R and f g in R alpha, then lambda f plus mu g is in R alpha. Okay, see, it's not only a vector space. Remember, from R alpha to R, I have a function now. What is the function? You give me any function f which is in alpha integrable, I can map it to the real number interval a to b f d alpha. This is a real number, right? So I want to know this. If I know this is a vector space, I would also like to know what kind of a function this mapping is. Obvious question to ask is whether it is a linear. Yeah, very good. So these are the questions we want to address. Okay, now before going, let's look at thing. We define R alpha for any function, not necessarily increasing, right? Okay, so when I want to show that this is a very gentle vague remark, you will see its use, because this is the kind of thing you should have that kind of intuition. See, suppose when I want to say some function f is alpha integrable, okay, right, there are two ways of doing. One may be using Riemann sum approach, the other one is Darboux sum approach, that is upper and lower sum. Okay, this is the first definition, this is the second definition, right? Using any one of them, I may show f is alpha integrable. But remember, there is something very interesting. Again, let's go back. See, you should always keep mathematics as a single unit, okay, not separate entities. Do you remember, if I have a sequence xn, when I say it is convergent, then I would Okay, then if I know the limit xn converge to x, then I have to only estimate mod xn minus x. I have to show it goes to 0. You understand that? But if you simply want to show xn is convergent, right, if I want to show the sequence xn is convergent, for some reason I know xn converges to x. So to show xn is convergent, what all I have to show is mod xn minus x goes to 0. Do you understand? But if I want to show only xn is convergent, I don't have any idea what the limit is, then what will I do? I will do the Cauchy. Right? I will show that the sequence xn is Cauchy. Do you understand? So similarly here also we have the same thing. Yeah. Okay, now let's go back. So I want to show if all f and g are integrable, lambda and mu are real numbers, lambda f plus mu g is an alpha, and I also want to know whether it is linear. What does that mean? That means integral lambda f plus mu g d alpha, of course a to b, I may forget to write, but okay, this is lambda times a to b f plus mu times a to b g, this is d alpha. You understand? So it's something like xn converge to x is already known to me, right? If I want to show this integrable, so I also have what the integral should be, then I should only try to estimate this. You understand? In such case, given the two definitions, Riemann sum approach and Darboux sum approach, what do you think will be very natural for us to look at? Remember, in Riemann sum approach, okay, the integral is specified. That is Riemann sum minus some real number in modulus blah 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 blah. You understand that? So what is the very obvious thing to do? See, this is how you learn mathematics. So it's very interesting if you begin to think like this. So what I want to do is I have to show lambda f plus mu g. Therefore the obvious thing is to take the Riemann sum approach. Okay, therefore Riemann sum of this with respect to the partition P, with respect to set of tags P, and with respect to alpha, right? I want to say this minus this fellow, right, lambda integral a to b f d alpha minus mu integral g to d alpha a to b. I want to show this is less than epsilon, okay, for all partitions Q which are finer than fixed partition P. You understand this? That is, to show this is integral and this it is integrable and the integral equal to this. So what am I going to do? Since I know the integral, the obvious guess is you give me a limit epsilon positive, then I have to find a partition P, so that for every partition Q which is finer than P and for every set of tags T, this Riemann sum minus this number is less than epsilon. Do you understand this? Right. But what? So what do you think I have to do now? Yeah. So again the same thing. Suppose I know xn converges to x, yn converges to y, then I want to show, let's say, lambda xn plus mu yn converges to lambda x plus mu y. What is that I have to estimate? I have to estimate mod lambda xn plus mu yn minus lambda x minus mu y. Okay, so all of us are intelligent, right? The natural thing is club these two things together, club these two things together. Then I know how to do that. You understand? The same thing. So similarly here, what should I do now? What should I ask? What is the question I should ask? So this is the Riemann sum of, yes, whatever it is, okay, lambda f plus mu g q t alpha. What is the question you should ask? Okay, let us write it. Okay, if I can write it as intuitively like this, I would like to write it lambda times sf q t alpha plus mu times g q t alpha, then I am happy. Do you understand this? Yes. So you have to check whether it happens. So it is, let us do this object, okay, equal to summation lambda f plus mu g at what? At the tag ti into delta alpha I. Is this the definition? Do you agree with that? Yeah. But what is this? This is nothing other than, okay, this by definition lambda f is lambda into f of ti plus mu into g of ti, the whole thing multiplied with delta alpha I equal to 1 to n, and therefore that this is only the Riemann sum. Okay, therefore this is equal to lambda into summation f ti delta alpha I plus mu into gti into delta alpha I, right? Therefore modulus of s of f q t alpha minus lambda, let me call the integral as a minus mu b. Okay, you know what is a and b. Okay, I don't want, so that it will save my time. This is same as, but what is this object? This is lambda times s of f p or q, whatever it is, q t alpha. This is mu times g q t alpha, right? Therefore this is equal to lambda into s of f q t alpha minus a. Okay, so I can write it less than equal to plus the other one s g q t alpha mu into mod mu again. Okay, mod mu times minus b, right? Now what do I know? Okay, this I want to show is less than epsilon. So how will I make sure this is less than epsilon? I can make sure this is less than epsilon by 2. This I have to make sure it's less than epsilon by 2. That again, how will I do that? I know that a is the integral of f, alpha integral of f. Therefore, okay, given epsilon by 2, I know there is a partition p1 so that for every q1 greater than or equal to, for every q greater than or equal to p1, yes, f q t alpha minus a is less than epsilon by 2 times 1 plus mod alpha, mod lambda, because lambda could be 0. I'm just writing it. You follow that? Yes. And similarly there is a p2, so that for every partition p2 and set of things, yes, g q t alpha minus b is less than epsilon by 2 into 1 plus mod mu. Do you agree with that? So what do you think I will do? Take p equal to p1 union p2. Okay, now take q to be any partition which is finer than p. Therefore q will automatically be finer than p1 as well as p2. Do you understand that? Yeah. Therefore every such partition q which is finer than p, where p is p1 union p2, yes, f q t alpha minus a is less than epsilon times 2 times epsilon by 2 times 1 plus mod lambda. Are you following? Therefore come back to this. Therefore what do I have? This is less than mod lambda into, okay, epsilon by 2 into 1 plus mod lambda, and similarly mod mu into epsilon by 1 plus mod mu times 2. So this is times 2, not square. Okay, therefore this is less than 1, epsilon by 2, this is epsilon by 2, therefore I go proved it. Have you understood the proof? Okay, pause, review, proceed. The proof is extremely easy, but the basic idea is very nice. You see that? So instead of going through proof line by line, you should have first some kind of an idea, method of attack. What? Okay, I have two definitions. Which one I want to use? Why I want to use it? Like that. And second thing is, Darbo's may be imposed upon us if I have to use alpha is increasing also. You understand? That we'll see. Don't worry at present. Okay, go through the proof. Okay. So do you think I have proved both the things? What I have proved? I have proved lambda f plus mu g is alpha integrable, and its integral is nothing other than lambda times integral of f plus mu times integral of g. Okay, so we proved both the things at one shot. So what is the next result? Next result is something very, this is not in a general Riemann integral, if you have gone through a course in Riemann integral. Now suppose alpha and beta from a to b to r be bounded functions. Okay, let us consider them integrators, right? Yeah. Now let us put sigma equal to alpha plus beta. Then sigma is also a bounded function, so I can use as an integrator. Yeah. Now what is that I want to ask? I want to say, suppose f belong to r of alpha, also it belong to r of beta. Then I want to know whether f is in r of sigma, and not only that, and what is ft sigma. You understand those? Is the question clear? Yeah. Now f is alpha integrable as well as beta integrable. Then I want to know whether f is sigma integrable. Okay. How many of you can think what is going to happen? What do you think? The answer should be, see, now I have to make a guess, right? As I said, whether I want to use Riemann sum approach or Darboux sum approach. Okay, but Riemann sum approach, then I should know what is integral of f d sigma. What is your guess? My guess would be yes. How many of you can guess? It is a to be f d alpha plus a to be f d beta. You understand? This is my guess. Yeah, right. So what is the natural thing? Riemann approach, right? And what is that I would look at? Yes, f with respect to partition p tags t sigma. And what is that I want to say? How it is related to this minus this object. Let me again call it a and b. Minus a minus b. I want to estimate, right? But what do I know how to estimate? I know how to estimate S f p t alpha minus a, and similarly S f p t beta minus b. I know how to estimate. So what should be my wishful thinking? From whatever you have seen the first one, you should be ready with the answer, right? Yes, it is S f p t sigma is nothing other than, yes, I'm here waiting for your answer. That's it. If this is true, the proof is very clear. Do you agree with that? Yeah, good. But this is a trivial algebraic thing. What all I have to do? See, the only thing where sigma comes is delta sigma I and delta alpha I and delta beta I. So I want to know what is the relation between these two things. What is delta sigma I? It is sigma of xi minus sigma of xi minus 1. But what is sigma? It is alpha plus beta of xi minus alpha plus beta of xi minus 1. But what is this? By definition of addition of function, this is alpha xi plus beta xi minus alpha xi minus 1 minus beta xi minus 1. So all of us are reasonably intelligent, so we know how to term them together. Therefore delta alpha I plus delta beta I, right? Therefore what will I have? F of ti into delta sigma I, which happens to be f of ti delta alpha I plus delta beta I. But that is equal to SF p t alpha plus SF p t beta. Now can you complete the proof? Yeah? Okay. I'm sure all of you know how to do that. Exactly similar to the last thing. Okay. Note that if you are adventurous, you can also do that. Okay. Multiply by alpha, etc. But that's the same thing. What I mean? That is, multiply alpha by lambda, multiply beta by mu scalars, then sigma equal to sigma equal to lambda alpha plus beta mu beta. but exactly the similar thing, so one shouldn't waste time on such thing. Is that okay? Yeah, please go through it. So please pay attention. In both the cases, we did not want alpha to be increasing. The integrator need not be increasing. It could be any bounded function. As an integrator, I could still get the first two conditions. Okay. Now the third thing, that's also equally easy. Okay. Suppose I have A, B, and C is a point strictly in between. Need not be a midpoint. Okay. The picture always looks like a midpoint. Okay. It need not be. Okay. And suppose again alpha is a function from AB to R, bounded of course, and suppose f is okay. Now what are the things? See, now f is a bounded function A and B, therefore it's also a bounded function on the interval AC, and alpha is a function from AC to R, also a restriction, and similarly alpha I can restrict to CB, it's again a bounded function. Therefore what are the things I can talk about? R of alpha. Okay, now I will specify the domain AC, R of alpha, domain CB. Also I can define R of alpha, the domain AB. Do all of you understand this notation? What does it mean? This set of all functions from the interval AC to R, which is alpha integrable. Here alpha is a restriction of alpha to this interval, and similarly R of alpha CB. This set of all functions from bounded function from CB to R, which is alpha integrable, and so on. Yeah, so let us just write it. So it may be better to write some, give some name. So let A to B d alpha, and A to C f d alpha, and C to B f d alpha. These are the three integrals. Assuming they make sense, I do not know. Okay, suppose this makes sense, all of them make sense. What do you expect should happen? Think again in terms of geometry. Okay, I have A, B, and this is C. Okay, so what do? I am looking at this area and this area and this total area. What do you think they should happen? Yeah, they should add up, right? So I should expect this happens. Right? This is the vague. We still have not formulated the statement of the theorem. Okay, we are just playing. Okay. See, any kind of science is, just by experimenting and exploring, okay, observing, you formulate. So that's what we are doing. Okay, so so this is my wish. I think this should happen. So let us try to say what with a little more precise sense. What you want to say is, let C be a point strictly in between A and B, right? Now there are three integrals. Okay, f is alpha integral on the interval AB, f is alpha integral on the interval AC, f is alpha integral on CB, etc. These three notions. What I am saying is, out of these three integrals, assume two integrals make sense, then the third integral makes sense, and this equality holds. Do you understand this statement? Shall I write it? So assume two of these integrals make sense. Of these three integrals exist or make sense, or exist. That is, either f is alpha interval A to C and f is alpha interval from A to B. Then what I want to say, f is alpha interval from C to B. And now all the three intervals exist. What should be the relation between them? This is the relation. Okay, and star holds. So this is the theorem. Have you understood this statement? Okay, proof is easy. Okay, there are three cases, right? So given the three intervals, two of them exist, therefore three choices. But we will work with only one case. The other two cases are similar. All textbooks and our teachers, everybody will leave it as an exercise for you, and usually no student does that either. Anyway, okay, anyway, let's do that. Okay, but the most important case is when I suppose A to C exists and C to B exists, then I want to know whether A to B exists, and of course the equality also. This is a statement you want to do. Okay, this is one of the statements. You understand that the two intervals on the right side of star makes sense. Then I want to say the interval on the left side of star makes sense and star holds. Okay, right. So what do I want? So again you see that there is no condition on alpha. It should be any function, and notice that we already have I want to know interval A to B f exists, and I know star holds. Therefore what is the best approach? Riemann sum approach, because I know what the integral should be. Therefore what should I do? I have to show yes f p t alpha, where now p is a partition of AB there. Okay, partition of AB, right, minus integral A to C of f d alpha minus integral C to B of f d alpha. I have to estimate. Do you understand that? If you give me an epsilon, I have to find a partition P, so that for every Q finer than P, this should happen. Is that clear? Yes? Then I would have proved the result. This. Okay. The integral A to B exists and it's equal to sum of these two. Okay. That's by definition, right? Okay. Right. Now how do I do that? Again easy. Now let us look at C, A, and this is my B. Okay. Now integral A to C of f is alpha-integrable on AC. Therefore I know there is a partition P1 here. Yeah. And similarly f is alpha-integrable on C to B. Therefore there is a partition P2 here. With what property? I'm sure all of you know how to write such things. Yes, P1 and whatever, if you want, call it T1 alpha minus A to C f d alpha. This is less than some epsilon by 2, whatever you want. Okay, let's not worry about that at that point of time being. Similarly, yes, f P2, the set of tags in C to B, T2 alpha minus C to B f d alpha is less than epsilon by 2. Right? Now all of you know the general trick. What is that? Take P equal to P1 union P2. Yes? Okay. Now notice that C will be an element of P all the time. Did you understand that? Yes? Therefore, if I take any partition Q which is finer than P, C will also be a point of Q. Yes? Oh, instead of coming to the new page, I've done something, so it's very bad. Okay, what to do? It will be easier if I do from there, but anyway. Oh, here it is. Okay, yeah, good. I'm happy. Yeah. Okay. Now let us look at now what is the next question you should ask? Yes, f p alpha t. Okay. Now let's look at this is my A B, right? Now take any kind of tags, right? Minus integral A to B A to C f d alpha minus integral C to B f d alpha. Or sorry, again Q is finer than P. Yeah. So again, I'm sure all of you now know the trick, right? I know how to estimate S f P1 or anything Q1 which is okay alpha t. Notice that I want, okay, suppose Q is any partition which is finer than P. Then I can generate a partition P1 of AC. How will I do that? Take a Q intersect with AC, right? Remember C is already there, therefore it will also be a point. Yeah, therefore this is a partition. And is that clear that P1, okay, maybe I should say P1 dash, because I already fixed P1 and P2. Yeah, you understand that? For the given epsilon I fixed P1 and P2, so I don't want to do that. So given a partition, oh maybe, oh that's very good, very good. I call it Q1, very good. Q, yeah, Q1 is Q intersection this, and Q2 is Q intersection CB. So I get a part, okay, tags from A to C. You understand this? Yeah. Now the first thing you should notice is Q1 is finer than your P1. Why? Because all the points of P1 are already on P, therefore they are already in Q. You understand that? Therefore all points of P1 are already in, all the nodes of P1 are already in P, but Q contains P, therefore all nodes of P1 are already in Q. Therefore Q intersection AC will contain P1. You follow that? Sure? Okay. Is it alright? Okay. And similarly Q2 will be greater than or equal to finer than P2, right? You follow that? Okay. The next question is, what's the relation between S, F, Q, T, alpha? Now I have S, F, Q1, T1, alpha, and S, F, Q2, T2, alpha. And I'm sure that you understand what is T1. T1 is T intersect with the AB, AC. That is set of points in the tags of, you know, this is a tag in Q, and look at only those tags which are in the interval AC, call it a T1. And similarly other one. Okay, so you know what is T1 and T2, right? Now Q1 is finer than P1, Q2 is finer than P1. Therefore what do I know is this interval minus A to CF d alpha, this will be small, this C interval C to B F d alpha, this will also be small, right? Okay, but what I want is this, this is small. So what is the natural thing I should do? By now all of you are adept, very comfortable with this. What do you think? I should show this equal to this plus this. Okay, this is what I want to show. But that's a trivial checking, right? This pure algebra. Do you agree with that? Yes? Okay. So check. Yes. F Q T alpha is SF Q1 T1 alpha plus SF Q2 T2 alpha. Just look at the definition, it follows. Okay, so now are we through? Because this minus this is same as this minus this plus this minus this, therefore put a modulus, that will be less than or equal to modulus of this object plus modulus of this object, but this is less than epsilon by 2, this is less than epsilon by 2, etc, etc, etc. Okay, you can read my article or any book, this kind of thing. Okay, so pause, review, proceed. Okay, now how many results we have proved? We have proved 3 results. One is linearity and linear map property of the integral. F going to integral F is a linear map. Okay, that's first one. Second one is I can add 2 integrators, integral with respect to the sum of integrators equal to sum of the integrals, right? Integral of F with respect to some integrator equal to sum of integrals with respect to individual integrators. It's quite a mouthful, right? Integral F d sigma equal to integral F d alpha plus integral F d beta. And the third one is take the interval, okay, put a point in between, then I have 2 subintervals, the union is your original interval, then integral of F over the full equal to integral of sum of the integrals over the subintervals. Okay, that's it. One version we have proved, the other version is also equally easy. Understood? Now the fourth one I want to prove. This is what is called monotonicity. Monotonicity meaning, what do you mean? If m, okay, less than n, you want the sequence xn to be less than xn. Then you want to say xm is increasing, right? The sequence xn is increasing, right? Okay, that's a monotone. So here, what is the thing you want to do? You want to say the following. Suppose f is a function from a, b to r, again bounded, and assume f is greater than or equal to 0 on a, b. Okay, and alpha from a, b to b is an integrator. Then I would like to know f d alpha, okay, is greater than or equal to 0. This is all I would like to know, but be careful, I am not claiming that yet. Okay, yeah, do you think this will be always true? No. So we want alpha to be increasing, then I don't need bounded. You see that if alpha is increasing, then interval f d alpha is positive. Because if I take alpha of x equal to minus x, right, that interval f d alpha, suppose it exists, what will be, okay, let us take beta x, okay, alpha x equal to x, right? Then what we already saw, d beta is nothing than f d alpha, right? Therefore if f is let us say equal to x and 0 to 1, this will be positive, whereas this will be negative. Are you following? Without minus sign, this will be positive. Therefore f d beta will be, interval f d beta will be negative. So therefore I should not expect this always true. What should I expect is if alpha is increasing function. Is that okay? Right. So now what do you want? So should I use Riemann approach or Darboux approach? Think. Naturally I should use Darboux approach. Yeah? Are you convinced? Yes or no? Yeah. You can also use Riemann approach. I will explain it in a minute, but it's all here. The obvious thing will be positive. Why? Because for any partition P, okay, remember my interval f d alpha a to b is the LUB of LFP alpha, right? Of course it's also GLB of UFP alpha, but again I want to use LUB. Why? You will see in a minute. What do I know is LFP alpha by definition is summation mi minus mi into delta alpha I. You understand? But this is always greater than or equal to 0, and since alpha is increasing, this is also greater than or equal to 0. That means LFP alpha is greater than or equal to 0. Are you following this? How did I know mi minus mi is greater than or equal to 0? That is always true. Yeah, it's always true. Sure? Do you follow that? So what I need to do is only delta alpha is 0. Therefore this will be always positive, and therefore each of the lower sum is non-negative. Therefore its least upper bound will also be non-negative. But that is, since f is alpha integral, that is the integral. Therefore it is non-negative. Is that clear? Here also you can see UFP will also be non-negative, but the GLB you have to prove it's not negative. It is also non-negative because it's going down. You understand that? Just to try to understand mathematics. Suppose if xn is non-negative, if xn converges to x, we want to say x is greater than or equal to 0. You understand? Yeah, the way to prove that is one. So if x is negative, then you arrive at a contradiction. Take x by 2, then after certain stage all my extents will lie here, they are all negative. That's a contradiction. It's nice to go through the proof. So you can mimic that proof to show, okay, u of p alpha is also greater than or equal to 0, and its GLB also has to be greater than or equal to 0. You can prove that, but I will not suggest it. Okay, and the similar thing also you can prove with respect to Riemann sum, because yes, f p t alpha minus something, okay, I know it exists, but this is always greater than or equal to 0, because this is summation fti delta alpha I. This is positive and this is positive, therefore this is always positive, and this is integral a to b f d alpha. Okay, suppose a to b f d alpha equal to some let us say theta, which is less than 0, right? Now again take theta by 2, okay, therefore there is a partition such that this should be less than theta by 2. Okay, I'm going fast. If you have gone through my sequence thing, you will be more comfortable with this kind of logic, otherwise you will struggle, right? So I have theta, I have 0, this is my theta by 2, which is negative. Therefore after, for all q which is greater than or equal to p, for all partitions, that fellow will be within, this is your theta, this is your integral f d alpha, you understand? This is negative, therefore it will all lie here. For all partition q finer than p, for any tag, set of tags t, this will be in this interval. That means this has to be negative. That's a contradiction. Exactly the same proof as you did for sequences, but this is the simplest and easiest proof. But it has an obvious corollary that is most important. What is the obvious corollary? Suppose f and g are here and alpha is again increasing, and fg belong to R of alpha, and let's say assume f is less than or equal to g, then yeah, can you guess what is that I want to say? This is obvious. Why? Let us look at g minus f. Since f and g are integrable with respect to alpha, and for any integrator alpha we know g minus f is also in R of alpha. So in particular for thing. And what do I know about g minus f? G minus f is greater than or equal to 0. Is that okay? Yeah. So what is that I have done now? G minus f is greater than or equal to 0. Therefore integral of g minus f d alpha a to b must be greater than or equal to 0 by the first part. But then again, by the linearity of the integral I can use, this is nothing other than a to b g d alpha minus integral a to b f d alpha, that is greater than or equal to 0. Therefore the result follows. Okay, have you understood? Okay. I'm sorry, here I made a goof. Nonsense. See, since I had been working with UF etc., remember this is simply mi. Okay, and mi is of course greater than or equal to 0 because the function f is non-negative. I was somehow, when I was going through the proof, something was bothering in my mind, but okay, I just skipped it. That's why I came back to you. Are you following what I'm saying? LFP is just little mi, but f is always non-negative, therefore the infimum will also be non-negative. You understand that? Now the rest of the proof is okay. Okay, what I wrote here was wrong. This was wrong, but this is correct. Mi greater than or equal to 0 into delta alpha. That's okay. See, this is what happens. Sometimes you get carried away. Okay, since I have always been working with u minus l, here also I did immediately wrote summation capital M small m. Okay, right. I hope all of you understood this. Okay, that was a goof, but luckily I corrected it. Otherwise it will be a real disaster. Yeah. Okay, right. Now the next thing I will prove an important result. Okay, this is a technically superior result. Okay, and most often textbooks will try to avoid, and teachers will try to avoid. What is the thing? I will just state it. What is the point of stating? Just quickly, this is a b, okay, a function. It takes values in little m to capital M. Okay, and from here I have a function g which is continuous to R. Then I have g comes to f. If f is belong to R alpha, again alpha is increasing. Okay, then g comes to f also belong to R alpha. This is what we want to prove. If you prove that, now notice that x going to mod x is continuous function. Therefore, if f is in R alpha, mod f is in R alpha, and f squared is in R alpha, because not R alpha, because x going to x squared is also continuous function. Therefore, x going to fx, that goes to f of x squared, that is f squared of x, that also belong to R alpha, etc. And from this we can deduce if f and g are alpha, if f and g are in R alpha, f times g is in R alpha. All these things will follow. So I only have to prove this result. This result is a fantastic result. Do you remember? We already said as a strategy, u minus L, upper sum minus lower sum, and I want to estimate, we may have to use divide and conquer. This proof is going to illustrate it very beautifully. Okay, stay tuned. We will meet in the next lecture. We will do that. Okay, perhaps within about half an hour I will try to do it. I will try to think through the proof. Then later I will also tell you how to write a rigorous book as you would find in textbooks. Okay, and you will really appreciate. Okay, stay tuned. We will meet again. Bye.